Hi everyone, I'm Alfie here at St Andrews, and today I'm going to talk about some of the early results I've got from some cosmological simulations I've been doing. So I'll outline the motivation for why we would want to look at a new cosmological model, focusing more on kind of the large-scale issues. Then I'll give an overview of the model I'm looking at, vHDM. I'll talk a bit about my simulations, and then go over the early results I have. So for why we might want a new cosmological model on the large scales, basically the first part is there's evidence that early structure formation is enhanced. So we see there's bulk flows higher than the ΛCDM predictions. If we look at clusters such as the bullet cluster and Gordo, they're quite massive and they're colliding quite fast. And then there's also evidence, as we saw the past few days, in galaxies. We have these high redshift galaxies and also issues with supermassive black holes growing quite quickly. And another large-scale issue we're starting to get more evidence of is we see more supervoids on kind of 100 megaparsec scales than we expect. So generally, if we look at the integrated Sachs-Wolf effect, there's an imprint from these kind of these scale supervoids, which is much larger than the ΛCDM prediction. And then also in the local universe, we see evidence in near-IR, X-ray, and radio observations that there's an underdensity in the luminous matter, at least during the amount of stars we expect, which is for the local hole, and again has about this 100 megaparsec radius. And then the most famous one, I think, of course, is the Hubble Tension, what basically are CMB determinations, or kind of our indirect determinations of the Hubble constant, and the more direct local determinations. The error bars have collapsed down a lot over the past few years, but they've collapsed down in different places, and this is leading to a more than 5 sigma disagreement between the CMB determination and the more local determination from supernovae. So onto the model I'm working on, vHDM. What actually is it? So the new part is MOND, and hopefully everyone here has some understanding of what MOND is. And the only thing I'll mention about that for now is we're using this simple interpolation function for the MOND gravity. And the other component is hot dark matter. So these would be dark matter particles with a low mass, which means they have high thermal velocities at recombination. And so they free stream out of small scale density perturbations. And that should mean we only have baryons really on small scales. And then in this model in particular, we assume they're 11 electron volt scale neutrinos. So the key assumptions we want to make here is that the ΛCDM interpretation of the CMB is, I'd say, mostly correct here because we assume it's essentially identical, except that we replace all the dark matter with our scarab neutrinos. And this should be fine because the one of the Planck papers, I think, from 2015, state explicitly that they looked at scarab neutrinos replacing the CDM component in their fit, and with the current data, you can't tell the difference between CDM and 10 electron volt scarab neutrinos. So anything heavier than that will fit the CMB fine. We also assume there's an FRLW background metric, so we have the same expansion rate history as ΛCDM. And then finally, that MOND effects are negligible with the early universe, which again leads back to kind of assuming we have essentially the ΛCDM CMB. And so, yeah, that should all work fine. So we have this model, but why combine MOND and hot dark matter in these ways? Like, kind of what's the point? So the first point is with hot dark matter, all our galaxies should only be baryonic, and therefore have be determined only by the baryonic matter and MONDian gravity. So this means essentially our galaxies are completely MONDian in nature, and we already know that MOND kind of does better, a lot better than ΛCDM in the galactic scales. So that's the first kind of thought process behind this. Next is we have a missing matter problem on cluster scales in MOND. So if we just take the baryonic matter and our normal MOND of gravity, put them together in clusters, there's still a missing matter problem there, which again we've seen earlier this week. And so the dark matter comes into play again on these kind of cluster scales to kind of make up that missing mass issue. In clusters should end up looking quite similar to ΛCDM clusters. And then also, as I said before, the CMB is easily explained because it's basically the ΛCDM one. And also, we should expect the MOND gravity to enhance structure formation. And the hope is that will kind of ease some of the issues related with the early enhanced structure formation. And one other thing I'd like to mention quick is the bullet cluster, where we see an offset between the baryonic or the gas component and the gravitational lensing, which can be a bit difficult to explain in theories where you only have the baryons and modified gravity. But again, this should be more natural in this new HDM model because we have the dark matter on the scales. So again, we get to the same explanation as you would have in like a ΛCDM scenario where the gas collects in the middle, the dark matter can pass through during the collision and lead to this offset between lensing and where the gas appears to be. So that should hopefully work as well. And then also there's another question of people have worked on this model before and that kind of stopped for a bit. So why are we returning to it now? And it's basically because the more modern observations we have now seem to be a bit more amenable to this model. So the first simulation paper, one of the first simulations on this model, Angus et al. 2013, actually produced analogs to the local hole before it was observed. And unfortunately, because they produced these analogs before the observations, they kind of assumed that that was an issue with the model, and it was part of the reason why they stopped working on it. Another benefit of having a model which produces these local hole analogs is it might provide a resolution to the Hubble tension. So the way this would work is you have, as matter kind of flows out of the void to the void edges, it will provide a systematic enhancement to the local determination of the Hubble constant. So basically things flow out of the void, they have an additional recessive velocity from us due to that, and that should enhance the local determination of the Hubble value, and they provide a resolution to this tension. And also, a more recent analysis found the rate of analogs to like the Gordo cluster, these clusters which are a bit too large and collide a bit too fast in ΛCDM, should be fairly consistent with this model and simulations in this model before. So my simulations use the Phantom of Ramses code, and I'm doing cosmological collisionless N-body simulations. So basically, assuming everything is kind of like this dark matter, because I want to probe the large scales really. And the MOND is implemented in these simulations by solving the QMOND Poisson equation rather than the Newtonian Poisson equation. And so the runs I'll talk about today here have an 800 code-moving megaparsec IH box length and have 256 qubit particles. These are lower resolution than I would like because these are kind of early results and I'm just testing the model and seeing what's happening. But I hope to run some high resolution ones soon. And then just for some more details about how these simulations are actually done. We initialized them Z equals 199, where the universe should still be mostly Newtonian actually in this model. And the initial conditions are produced with canon music, which are fairly standard codes. And if you want to see any of the codes we've used, you can find them here. And then I'm also going to talk about, in addition to like ΛCDM and new HDM, this lambda HDM and new CDM models not because we expect them to be realistic in any way, but because they can give us an idea of what the changes we're making between ΛCDM and vHDM, what those changes actually do to our results. So the vHDM here is Newtonian gravity with hot dark matter initial conditions, and the new CDM is the MOND gravity with cold dark matter initial conditions. So we move on to kind of what these simulations look like. This is a column density projection through the whole box for each of my different simulations. So you can kind of see here for the, if we compare between the different models, the Newtonian ones on top, we can see have a lot less structure than the MONDian components on the bottom, which is kind of what we expect, so that's a good start. And then also, if we compare the CDM to the HDM models, you can see the structure in the HDM models tends to be more large-scale. You tend to have more large-scale structure in these, whereas in the CDM, everything collapses kind of into smaller halos. And again, that's kind of what we expect intuitively. So that's a good sign for the start that the simulations are working. So if we try and quantify now how structure is forming, we can look at the cumulative halo mass function. And a surprising result here is if you look at this green line and the red line, this is the lambda HDM and the new HDM, and compare it to the CDM simulation. So the blue line is lambda CDM and the orange is new CDM. You can see actually the shape of this cumulative halo mass function is determined more by your dark matter model rather than your gravity model, which was kind of surprising at first. So you can see here, we have kind of in the HDM models, the function is a lot flatter, and this is because basically there's a lot less small scale structure. All of our mass is kind of fallen into larger scale halos, and that's why you get this. You have less halos in total, but much more of these high mass halos. And also comparing between now the Newtonian simulations and the MOND simulations, you can see, of course, comparing the MOND simulations have a lot more halos, all masses basically, which is again, like we expect the structure formation to be faster. So this is good in the sense that it's working as expected. But then we start to have issues when we compare now the MOND simulations to the observations. So you can see here the lambda CDM, this brown line is kind of what we would expect a lambda CDM N-body simulation to kind of look like. So you see our simulation deviates a bit here, and I think this is a resolution issue because at kind of these mass scales we're kind of at the resolution limit of the simulation, the spatial resolution, I should say. But as we kind of escape that resolution limit, you can see it starts to hit this expectation more. But this grey line now is the observed cumulative halo mass function up to about a gigaparsec. And you can see generically the HDM models are too flat, really, to fit this curve here. And also the new HDM and the MOND simulations overshoot the observations by quite a lot. Basically, they're producing too much large-scale structure. Before I move on to something else I should quickly note is, in order to make sure these comparisons here are kind of, we have a good comparison here between the simulations and observations, we have to apply a boost to the mass of the MOND halos. Basically, we plot here the Newtonian dynamical mass, which is you take the mass, the particle mass of the halo in the simulation, and you give it a boost, so you can compare between the observations and the simulations a bit more accurately. So that was a cumulative halo mass function for the whole simulation. But maybe, the MOND simulation didn't quite look like the observations. So maybe there's an issue with we've not quite reached homogeneity. So a way to test that is looking at octants of the simulation boxes, which I've got the plots here. And you can see basically for all the simulations, they're kind of, each octant is a very close cumulative halo mass function. Except in the new HDR one, there's one octant which is, let's say, 0.3 dex lower. So maybe at the 200 megaparsec scale, we've not quite reached homogeneity. But the key thing to note here as well is the shape of this function is not affected much by whether, the shape of the function is fairly consistent between octants. So you'll still have an issue here of the gradients can be kind of a bit too low and not quite fit the observations in the new HDM case. So another way to kind of have a look at how realistic the simulations are is by considering the peculiar velocities of our different halos. And you can see, between the Newtonian and MONDian simulations, you have an enhancement of the peculiar velocities of about 10 times, which is quite extreme. So as a comparison for what we should expect peculiar velocities to kind of look like, I plotted on the local group peculiar velocity on each of these boxes, on each of these plots with this dashed black line. And you can see halos with the local group peculiar velocity are very rare in our MONDian simulations. So we can calculate the probability of having a peculiar velocity less than the local group one in our simulations, and that probability relates to about 2.5 sigma disagree. Calculation leads to the local group peculiar velocity being about a 2.5 sigma outlier in these simulations for the MOND cases. It's a fair comment here, though, to say, because these are so large scale, that maybe if we want to test the local group peculiar velocity, it would be better to look at smaller scale simulations. So there's some complementary hydrodynamical simulations of smaller scales up on arXiv now by Wittenberg et al. 2023. And they similarly find that the local group peculiar velocity would be about a 2.5 sigma outlier. So this is kind of problematic for the model. And again, if we think beyond the local group to kind of where the observations are in general today, in ΛCDM we expect bulk flows to be about of order 100 kilometers a second, I think. Observationally, actually, this seems to be an under-prediction of the observations. So there's recent observations which suggest bulk flows reaching up to about 180 kilometers per second, I think, which is a lot higher than what you'd expect in ΛCDM. And even more recent ones, I think, again, on arXiv of up to even 400 kilometers a second, which again is a lot more than you'd expect in ΛCDM, and it's kind of bad. But it's certainly for like our MONDian simulations, these peculiar velocities are much higher than what we actually observe. So it's kind of, problematic for these simulations. And again, another way to think of this would be in terms of redshift space distortions. If we really did have peculiar velocities, on average, the most common one's about 5,000 kilometers a second. In terms of redshift space distortions, I mean, like estimating structure formation in a ΛCDM context, for those we would have gigantic masses for clusters. So this is kind of a bit high. So we have these kind of issues with these simulations. This model seems to be kind of unrealistic. It doesn't seem to represent the real universe quite well. So what can we do next with it now? How do we proceed from here? So I think the most obvious thing to do next would be to try and create a more realistic model. So we can look at increasing the scale neutrino mass so that we get a curve on the cumulative Halo mass function, which looks much more realistic. And we can also think about having a smaller enhancement to gravity, rather than our kind of naive application here of just extending MOND in its normal form all the way up to these large scales. So I started looking at increasing the scale neutrino mass, but I'm hesitant at the moment to play around with the enhancement to gravity, because I'm not sure there's enough of a theoretical basis for me to work off there. That essentially at the moment I would have infinite freedom to do what I wanted with the gravity law, and I'm not sure that's perhaps the best way to deal with this. We complain a lot about freedom in hydrodynamical simulations, tuning the simulation to the observation. And essentially, if I have full freedom to choose how the MOND gravity works on large scales, that's kind of a very similar issue. But something else we can still learn from these simulations, actually, is, if I head back quick, you can see in the new HDM case, at least, it looks like we're forming these kind of 100 megaparsec scale supervoids. So something we can still look at is what kind of signals do these supervoids we have in simulations imprint onto mock observations. So in particular, we can try and test whether a local hole solution to the Hubble tension realistically, if that kind of solution conforms with what the observations say. So there's been some recent suggestion in the literature that if you really do have a local hole of this, on a 100 megaparsec scale, then you'll observe a bump in the supernova data. Basically, when you transition from the void itself to the filament at the edge of the void, you get a bump in the supernovae data, and we don't observe such a bump in reality. But those that was in an analytic. They found that with an analytic solution in a lambda LTV context. So it would be good here to test. Do you actually find a similar bump in? Would you find a similar bump in the observations in these self-consistent simulations, or is that something unique to the lambda LTV? But if we do find, a signal like that, then that kind of would provide evidence against there being a local hole solution to the Hubble tension. So I think I went quite quick and I have a bit more time. So I'll briefly talk about part of our earlier assumptions of having a Newtonian early universe. So we can see this in, if we plot the medium peculiar velocity of particles in these simulations. We have this dashed dot line represents the expected growth of the medium peculiar velocity from linear perturbation theory. And then these purple dashed lines represent, there's an analytic prediction of when MOND effects should become important in these simulations. So we can see first off, the Newtonian simulations, they follow this linear prediction quite well, so that's good. And then this black line shows when we enter the dark energy era, and you can see this predictions for the matter era, and you can see they deviate from it in the dark energy era. So that's good. They certainly seem to be Newtonian. which are a Newtonian simulation, so we hope so. And then for the MOND simulations, again, we can see they follow this Newtonian prediction for the evolution quite well before the z equals 50 point. And then once they reach that z equals 50 point, they start to deviate and grow much more exponentially as the simulation box as a whole enters the MONDian regime. So I guess just to finish up here, the basic takeaway from the results so far seems to be this cosmology doesn't really ease the large-scale tensions, but it overcorrects for them. So just applying the full-strength MOND gravity to the large scales seems to over-enhance the large-scale structure formation, and using the hot dark matter causes an underproduction of the small-scale structure. So if we want to find a more realistic cosmology, we would want to think about making less drastic modifications. But even though we have these issues, we should still be able to extract some useful information from these simulations and start to test. Is the local void a realistic solution to Hubble tension, or do we need something else? Thank you.
How massive can you make the sterile neutrinos, where you have to worry about packing too many of them inside galaxies?
Yeah, so the limit, the theoretical maximum limit would be around 300 electron volts, but that's more to do with it's called the Tremaine gun limit, which limits the phase space density of the sterile neutrinos. If you go above around 300 electron volts, then your sterile neutrinos really start to enter your galaxies, and that will kind of mess up the MOND effects. But I can show quickly. So I've looked at implementing, I did 350 here, but 300 electron volt sterile neutrinos. And the purple line is very difficult to see because it essentially follows the CDM case. So you can kind of see they separate a bit here, but if you go up to about 300 eV, they shouldn't be in the galaxies too much, and it also looks it's essentially identical to like CDM on these large scales. But yeah, you can see still that the MOND gravity is maybe a bit too strong even in this case.
I have a related comment on the masses of sterile neutrinos. I think there is not much room to improve them because the experimental constraints from the Catling experiment are becoming quite tight. And I have the excursion plots in front of me, and for example for 300 electron volts there is just a very tiny window left, which is at very small mixing angles between active and sterile neutrinos. So there is a window left, but it seems it's shrinking, and so I have the impression that that option is probably not really viable.
Yes, I mean that's kind of another issue with this model is the available parameter space for the neutrinos is closing down, and it's not closing down the way you would want it to be for this model. So theoretically, 300 eV might make the simulations look more realistic on the large-scale structure sense, but I think you're right in that the model itself might become excluded in that case, that those sterile neutrinos couldn't even exist.
Yes, looking at your first two conclusions, or first 2 points, it looks like you've got the worst of both worlds, no? So I was wondering
Yeah.
what the general conclusion of that might be. Is it just a matter of having overcompensated and, you, as you say, go for less drastic modifications, or is it somehow a matter of I don't know, changing the corrections around or something? I don't know.
So I mean, I guess I guess it's difficult. It's difficult to kind of. I say here that you could make. Sorry. When I say about making less drastic modifications, I think what that really means is. I'm not sure you can. Yeah, you can't really extend MOND gravity all the way up to large scales in this context. I think it just it does too much. And then also, there's definitely going to be issues with, like fixing the stereo neutrinos, because basically it doesn't matter, it seems to not matter too much on what you do with the gravity if you have hot, or maybe, if you have anything like hot dark matter, it just seems to, you just don't get enough small scale structure. You don't have the initial density perturbations to actually make your galaxies there. So I'm being optimistic here, saying I'm being quite optimistic, saying that you could try and fix it, but I think realistically this might not be the best approach to try and fix the issues in cosmology.
Well, to Xavier, yeah, and to many in the audience, this is only a very preliminary attempt, which we just for simplicity use the simple mu function. All these clusters, the large-scale extra signal, will go away if we just completely cut out anything over A naught. I just turn off the scalar field for anything over A naught. All those stuff will not receive any benefits of MOND. It's because the continuity of the very gentleness of the smooth, simple mu function is probably the worst. It encourages a lot of marginal Newtonians to grow. So we need to explore more mu functions at the high acceleration end, where some of these are. Okay, sure.
I think just to kind of add to that though, you can. I think it may seem like a good idea to kind of try and curve the MOND effects on large scales, but I think really like a really deep other issue is that you can't. I'm not quite sure there's a way to have a dark matter that's hot enough that it doesn't affect your galaxies at all, whilst also having enough initial density perturbations to actually make those galaxies in the first place. I think it will be very difficult to get purely baryonic galaxies in a model like this.
Sorry, do you have some like a power spectrum you can show to illustrate the difference between LCDM and the new HDM? Initially.
I don't have the power spectrum, but I have the transfer function.
This is good. This is related. So yes, I agree with what you were saying, that you have, of course, no cold dark matter in MOND, and as a result, because the oscillations we see in the CMB imply a very low amount of power in the baryons, you can't see the formation of galaxies at high redshift in the standard way, of course, which is with CDM seeds. And this makes it extremely hard to form galaxies at high redshift. So I agree with what you were saying there. Regarding the issue of the interpolating function, it's extremely unlikely that an adjustment to the interpolating function will change anything here, because most large-scale structure is in the deep MOND limit. So really cutting off modifications to gravity above A0 slightly faster, using like the Magor-Lely-Schomburg function, for example, instead of the simple one, is highly unlikely to solve any of the problems with this cosmology.
Any more questions?
In the little plot I showed yesterday, or the day before, I had equality of cosmological term and matter term to be at minus redshift of 1.7. That was because I took the density, matter density to be that of the baryons. When you take it to be closer to 0.3, then of course you move it to less, the redshift equality to less than 1. And that's what you've done here. But the question is, how compelling is this argument that the matter density is 0.3? Well, it's consistent with the supernova results, the supernova statistics. But how compelling is that? That's what I wonder.
I guess in terms of when I'm thinking about kind of how we constrain like the matter density parameter, my mind I think goes more to the CMB first with that, because I think at least the strongest evidence for me that you kind of have this significant dark matter component, or maybe like the dust in the Gordo model, is the third peak in the CMB being about the same height as the second peak. I'm not so sure, like you're saying with the supernovae data, I guess I need to read up on that more to kind of decide how much I trust it. But I think certainly with the CMB, you need, to explain that it's difficult without introducing a significant, something that acts like dark matter, that produces a significant part of the density of the universe.
I'm just saying, it's remarkable to me that cosmological term equals the matter term right about now. I mean, very close to now.
Any more questions?
I agree that with the supernova data alone, it's probably hard to distinguish between omega lambda of 0.7 and 0.95, which is again an equivalent way of looking at your question. So regarding what Alfie was saying, yes, there is, at least in this model where you have essentially Newtonian gravity at redshifts above 50, you would need some mechanism to explain the high third peak in the CMB. But I'd like to add that also galaxy clusters, not just the bullet, but other more nearly virialized galaxy clusters, also show at the very high mass end a ratio of dynamical mass to baryonic mass of also about 5 or 6. And it doesn't make much difference whether you use MOND or Newtonian gravity in that case. But there are some analyses which have specifically done this in MOND, and the ratio is close to 5 there. So if you believe the omega b is about 0.05, then you typically would need omega m of about 0.3. But I agree that this is not immediately obvious from the supernova data alone.
Nobody cluster is much less than the standard cosmic ratio. With MOND, you need only a factor of 2 or less, 50% more. Once you correct for MOND, right? The amount of matter that you still need in MOND, the remaining discrepancy after you go.
I mean, the Pointer-Cottier and Silk 2005 paper showed that you need, which is explicitly in MOND, showed a ratio close to 5 times.
No, you're mistaken. They actually reach like 20% more matter that you need in clusters. I mean, the MOND, okay, so without MOND, you need a factor of 6, 7?
No, yes.
Okay.
But their analysis used MOND.
Is what?
One of their analyses used MOND.
No, but when you use MOND, the accelerations at the radius which they achieved is already a function of A0. So there is a...
Care of that.
No, so MOND corrects by a factor of 3, so you're not... No, Poincaré reached the conclusion that you need only a little more mass. not the fact, certainly not anything near the cosmic, the standard cosmic value.
They want to reference the latest constraints and papers by Ettore.
Yes. Can I just ask who of us is staying for the afternoon session, just to make sure that there's a point in staying?
No, sorry, staying, right?
What?
Huh? Staying.
Yeah, we're staying,
Yeah, yeah, I was worried, I joined the wrong team.
So many, shall we still hold the session? Yes.
Oh, yes.
Okay,
Yes.
so we meet again after lunch at 2:30.
Yeah.
And last 5 minutes to submit your reforms, please.